The last speaker of the morning is someone who has been active with the NBA for many years, almost since the beginning, I think. And Dr. Sotina has not been here for quite a while, and suddenly came back and joined us again in College Park. And she has been working, I know, in quantum mechanics for quite a while, and working on various aspects of the Schrodinger equation. And she'll be talking about that this morning with her talk. And I'd like to introduce you to Dr. Nina Sotina. Just give me a minute. Oh. What did I do wrong? Let's see. That is not the right file. Oh, I know what I did wrong. Hang on. Hang on. It's not. What kind of? It's in a. It's PDF, isn't it? All I got to do is rename it. I don't know how that happened. It's a PDF, right? Is it a PDF file?
No, no.
What kind of a file is it?
It's like PowerPoint.
Okay. I must have renamed it wrong or something. I don't know. I'm sorry. I thought I got everybody's.
It's good.
Good. Okay. There you go.
It's the next. It's the next.
Oh, you have the clicker.
It's my. This one. Oh no.
There you go.
The Schrodinger equation describes many observations very well, but there are still discussions about its physical interpretation. Currently, the probabilistic interpretation is the most common one. Its proponents, however, have a difficulty explaining the results of experiments with non-classical optical effects. It can be shown that probabilistic approach for the case of non-classical optical effects can lead to negative probabilities. It is one of the reasons to get rid of probabilistic interpretation of quantum formalism and to return to the idea of hidden variables. The probabilistic interpretation is also unable to describe the behavior of quantum system in living matter. It is known that a living organism molecules act as a well-tuned mechanisms that conflicts with the concept of molecule as a quantum system that is governed by probabilistic laws of quantum mechanics. Schrodinger was the first who noted this conundrum. It was one of the reasons why he was an opponent of the probabilistic interpretation of psi function. Schrodinger believed that psi function is associated with some real processes, oscillatory process in an atom. In 1935, Einstein, Podolsky, and Rosen put forward the issue of incompleteness of quantum mechanics description of physical reality and suggested the idea of existence of hidden variables. And it was proven that hidden variables can be either non-local. The non-locality is the existence of a connection between separated measurement devices, is essential to the theory of long-range forces, or a field wherein disturbance can spread at speeds greater than the speed of light. The latter was inconsistent with the theory of relativity. Furthermore, nobody tried to introduce such a field or medium to get rid of the probabilistic interpretation of quantum formalism. David Bohm was an Einstein student and the follower on the theory of relativity. He supported the idea of quantum non-locality and introduced the field of information physics. However, the idea of quantum non-locality is also non-consistent with theory of relativity, since there is a implicit postulate of the locality in it. The universe can be decomposed correctly into different and separate existing components of reality. To measure the speed of light, it is necessary that the receiver and transmitter will not only separate in space, but were also autonomous in their behavior. As a result, more and more physicists are inclined toward this interpretation, which was expressed by physicist David Mermin as shut up and calculate. I believe the way out of the crisis in quantum mechanics is in the return to the idea of hidden variables as a physical field, medium, ether, wherein disturbance can spread at speed greater than the speed of light. I will show below that the Schrodinger equation can be derived from the deterministic laws of classical mechanics. This derivation is based on the work of Russian scientist Chetaev. Chetaev showed an analogy between the stable motion of a mechanical system under the conservative forces and quantum processes described by Schrodinger equation. His work was not translated in English and is not known outside Russia. So it is present here, the English-speaking community for the first time. I will do it briefly. I will do briefly the derivation of the time-independent Schrodinger equation. Consider the motion of mechanical system under the action of conservative force does not depend on time explicitly. In this case, there exists the energy integral. This one, where U is potential energy, Q are coordinates, P are moment, and T is the kinetic energy of the system. The complete integral Jacobi equation takes the following form, such form. Let's make change variables. The following equations are correct in this case. The latter equation can be represented as follows, where L is operator, this operator, or using the energy integral can be written the form. Follows from the theory of stability that for the motion to be stable, operator L of S must be zero, necessary condition of stability. Thus, for the stable motion, the following is true. Let's search for solution of the latter equation in the form. In this case, the equation is written as Schrodinger equation. You can see. Note that Schrodinger was also used the Jacobi equation and the substitution 1 to derive equation 2. He found his substitution empirically as the one which yields the Rydberg-Ritz formula for the spectrum of the hydrogen atom. However, Schrödinger's approach did not clearly indicate that equation 2 contains extra solution, because this equation is not necessary condition of stability, not sufficient. Furthermore, it turned out that the equation 2 has more solutions than original problem. Probably that was the reason why Schrödinger approach that led him to his famous equation was not accepted by scientific community, and the equation 2 was taken as a postulate. Chetaev, however, noted that the Schrödinger equation contains other solutions besides those that are determined by the potential U, energy U. He gave a method that allows to find all the possible motion of the mechanical system under the action of the conservative forces, which as a necessary condition of stability have Schrodinger equation. Let me present now my derivation of Schrodinger equation based on Chetaev's method with a further analysis of the solution. So, assume that in addition to the primary forces described by U, there are also forces described by potential W. Represent the time-independent component of the psi functions S, where A is some real function of coordinates. In this case, the following equations are correct. As follows from the theory of stability for a motion to be stable, the expression operator F of S must be zero. The energetic integral can be represented as you can see. Consider 3 and 4 take the form of stationary Schrodinger equation. You can see if the additional forces F, Q have structure defined by these equations. Note that the forces F, Q are defined different corresponding to different solution of the Schrodinger equation. Forces of such type appear as an object is moving in medium or field as a result of object-medium interaction. Chetaev considers forces Fq to be small. However, I showed that they can be of the same order of magnitude as the primary forces. Let me demonstrate this for a hydrogen atom. For a case of one particle, the Schrodinger equation takes the form where v is the speed of particle. That is the Schrodinger equation is the law of conservation of energy of the stable orbit. Well, this is law of conservation. In a hydrogen atom, the electron moves along a circular orbit with the speed. The net force that provides an centripetal acceleration equals this one. The equation arises either this deterministic approach in which the characteristics such as trajectory or velocity of the elementary particle were introduced contradict the second postulate of quantum mechanics, collapse of the wave function. The answer of this question was given in article by Bohm and Halley. Bohm and Halley reviewed the quantum potential approach to quantum theory and showed that it yields a completely consistent account of measurement process. Let me remind you that Bohm supported the idea of quantum non-locality. He was noticed that the Schrodinger equation can be represented as a law of conservation of energy of stable orbits. He called the potential W the quantum potential. Bohm explained his quantum potential not as a physical quantity associated with the real forces in medium, but by introducing the field of information in physics. I would like to make a point here that inclusion of the information as a term in an equation that contains such physical quantities as time, force, and displacement looks like a logical inconsistency. Bohm, in his forward, often used an example of a ship controlled by shore to explain their ideas. Here, the ship controlled by radio signal is an analogy of quantum particle controlled by information field. In the case of ship, however, the EM signal turns on some real forces that act on the ship, such as interaction between the ship mechanism and field. I think that Bohm's information approach lacks the explanation of what is the nature of the force that changes the particle's motion, even if the control is done at a distance. Moreover, Bohm derives his formulas directly from Schrodinger equation. As was mentioned above, this equation contains extra solution that is such trajectories that not realized in nature. This should be taken into consideration when one analyzes concrete solutions. Another question is, how well does my deterministic interpretation of Schrodinger equation agree with the probabilistic interpretation? The answer to this question was in fact given by another Russian physicist, Kotel'nikov. As a starting point in his study, Kotel'nikov uses the Schrodinger equation and probabilistic interpretation of psi function. He raised the question: how can an elementary particle move according to laws of classical mechanics if its probabilistic behavior is determined by the Schrodinger equation? As a result of his mathematical derivations, he concluded that the particle should move under the action of two forces, a classical forces defined by potential U, and a quantum forces defined by quantum potential W. So the role of physicists is to establish correspondence between mathematical property of psi function and physical quantities. Psi function. Sorry.
It's okay.
Sorry.
Hey. Where are you at?
Сейчас.
Side 50?
Keep going, keep going.
Right here.
Right there.
Okay.
Sorry. The rule, no, it's okay. Psi function must change continuously along the trajectory and into the space surrounding the particle. From the latter formula, we can see that an oscillations with exactly the same frequency, epsilon over h, are at each point of space surrounding the particle. Unfortunately, the theory doesn't address the nature of this process yet. We can make some speculations only. In my opinion, the ether is similar in its properties to superfluid Gaussian 3. In this case, the following interpretation of mathematical formalism of quantum mechanics for a hydrogen atom can be suggested. This is the last. The center of mass of an electron in a hydrogen atom moves along the circle, and due to the Barnett's effect, a uniform precessing domain can appear in superfluid, which was observed experimentally. The frequency of precession of the domain epsilon over h. Simultaneously, the electrical polarization can appear in such medium.
Okay, great. We are open for some questions, but
12 minutes.
My daughter.
Sure. I'm going to start because I think what you're doing here is extremely important. I think this is really important work, but I'm not sure that everybody is understanding exactly what you're doing and why it's important. I guess one of the things I want to clarify exactly what this W function is. It's a function due to the not to the interaction of the particle, but with the environment, but with the particle within itself. Am I understanding that right?
W function. It is the
W function.
It is a Russia.
That's some real forces that appear in the equation, other than primary forces that described by potential.
Additional forces.
Additional forces that appear in the equation. That's here what's important to understand that this I didn't make conclusion from it was fun. All the conclusions are made from derived derivations, which started from classical laws, classical mechanics. Those additional forces appeared mathematically. It's all the only thing that the derivations were based on was Newton's law of physics, and then. Bohm, for example, also noticed those forces and as additional forces. He explained, as I mentioned before, those forces as information. Those derivations, if you use classical mechanics, then these derivations lead you to those additional forces. The interpretation might be different.
Okay. I guess since there's nobody else here, I'm going to go ahead because my goal here is to try to clarify exactly all what was happening here.
Okay. Yes. So the goal of my paper is just to try to derive Schrodinger equation just solely based on the laws of classical mechanics, and also assuming that there might be some additional forces if we take if we take physical vacuum as a medium.
Okay.
Then those additional forces, in my opinion, are created from as a result of the electron's motion, for example, through the medium.
But in the process of doing that, you also derive some additional terms, correct?
Yes,
that's true. Yes, in the process when I was doing it, I get additional forms that.
It's very exactly.
I'm looking
Yes.
for just maybe more physical explanation of what those extra terms mean.
So my opinion is that this proof for me that those forces come from that physical vacuum is not empty space, but it's some kind of medium. I believe that it's like superfluid helium-3 medium, and those forces looks like the forces when object is moving in the medium. That's very similar by their structure. It's very important to know that why I believe that it's from the medium, because the way the forces appear mathematically, that they depend on trajectory. In mechanics, it happens only when the medium exists. When object travels through the medium, then the forces depend on the trajectory. For example, when ship is moving, the waves that appeared behind the ship depends on the motion of the ship. And something similar you can see in this equation. Mathematically, they look very similar to the situation of the ship moving in the water. Like there is a medium.
That's ship, S-H-I-P, not sheep.
Oh, yeah, ship, sorry, my pronunciation is also right. S-H-A-B, right.
Okay, one last question and I'll be done. And that is, in what you called equation 4, which was pretty early on, you had, and it went so fast, but you had the product of two operators which would create cross terms in equation 4, and I'm wondering if those cross terms, how you interpret those physically. That I can find the slide.
Here, which one?
It was pretty early on. No, hang on, I'll find it. Find it with me. No. 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 There. No. Oh, come on. Did I go by it?
Yeah.
Oh, there it is. Equation 4. Okay.
Yeah, what I'm interested in is you're getting the additional terms, as far as I can see, are coming from the product of these cross terms, which doesn't appear in the original Schrodinger equation. So that's what I'm looking at. That's what caught my interest.
So the question is where?
The question is, what is the physical interpretation of the cross products which don't appear in the original Schrodinger equation? The Schrodinger equation only gives you the squares, but it doesn't give you the cross terms.
Yes, Schrodinger equation has them, and Bohm noticed them, but he didn't notice.
7 minutes left.
Basically, we're looking for such solution. We're looking for such solutions that they are, when you go through the process, they are not appear in the Schrodinger equation, but actually Schrodinger equation contains them implicitly, right? And Bohm noticed them. If you go from the beginning here, okay, that's why Schrodinger, the scientific community did not accept Schrodinger approach, because they noticed that Schrodinger equation has this extra solution. They are in there. If you go through the derivation, they are implicitly in there. So, and she, and I went like Schrodinger from the beginning, and that's why I get those extra solutions. Now the Schrodinger equation is taken by postulate. His approach was not accepted, but if you follow his approach, then you get those extra solutions. And also I showed that Schrodinger equation was called the mathematics necessary condition, not sufficient. It has extra solutions that do not realize in nature, which is very important.
Thank you.